what I'm going to talk about is some work I've been doing at the University of Kent and with colleagues at IOHK. And what we've been looking at is handling financial contracts on the blockchain that IOHK have built. So what I'll talk about is the language that we've designed. I'll talk about the environment that we've got in which you can interact with these things. And show we've got different forms of the language. We've got a textual form and a visual language you can use to play with these contracts. And also tell you a bit about what we can do, because this is a domain-specific language, the extra things we can do because of its specificity. So we can do analysis, we can do proof, in fact, of properties of classes of contract. And I'll also show you some examples from a standard for financial contracts produced by the ACTUS Foundation. So we'll run through those things, perhaps not in the order they are there, but pretty much I'll cover those. So the background for this is it's work done on the Cardano blockchain, which blockchain that has the currency ADA on there. And as an academic, working with an industrial concern can have advantages and disadvantages. You get real world problems to play with, but you can have the problem of not being able to talk about the work that you're doing. And one of the things that attracted me about working with IOHK is that they're very open. All their code is open source. We're encouraged to publish what we're thinking, what we've put into the framework. So there's no conflict there between being an academic and working with industry, which there might be with other companies. The other nice thing is that IOHK are a company who've taken functional programming very seriously. They've chosen to use Haskell as the prime development source for the blockchain, and also for writing smart contracts on the blockchain. What you can see over there, I'm sorry, the standard is wonderful. What you can see there is Haskell code, and that's the code that both runs, is compiled to run actually on the blockchain, and also runs off-chain in users' wallets. And all of that is written in Haskell. No new language there at all to learn. And also the model that I don't want to talk about blockchain in detail at all, but one of the model that IOHK have taken for working with the blockchain is what's called a UTxO model. So the way that funds transfer is simply by having outputs which are spent by joining them to a corresponding input. There isn't a notion of account on the blockchain itself, so there's no global state. All that happens is that money flows along an arc. Now, if that doesn't look like data flow programming, I don't know what does. So what you have here is as it were, a functional model of the blockchain. So that's by way of context. As I said, Haskell is used as a development environment, but also for Marlowe language, we use Haskell as the place in which to embed this as a domain-specific language. And I'll talk about that a bit later on. So if you look at, we've been talking about history of programming this morning. It's nice to show some old black and white pictures of computers. Now I'm showing you a slightly different one here than the ones we saw. This is the Leo, which was the first commercially used computer, certainly in the UK, I think worldwide. It was a version of the computer produced at Cambridge, and it had to work a lot harder than the original Cambridge one, which worked on physical problems, so typically took numerical inputs and produced numerical outputs. What this computer did was schedule baking batches for the Lyons Bakery. So it was used to solve commercial real-world problems. And they had immense problems producing machines that could handle inputs, produce outputs in an appropriate way. But the point is, the people who programmed that had to program in the language of the machine. With no high-level language, it was coding the machine. So there was programming, but very much at a low level. And as we moved through the 60s, people produced high-level languages, but it was the case then still that those languages might well be fixed to a computer or family of computers. They wouldn't necessarily be there wouldn't necessarily be portability between different manufacturers. But there were languages such as Fortran, Fortran, Algol, you know the languages. And those languages have but still they were presenting an abstraction layer over, as it were, what was happening was levels of abstraction were being put on top of what was effectively the machine. And I think you can see similar things happening in the Bitcoin area, in the blockchain area, that we have languages like Bitcoin script and Solidity and so on, which are general purpose languages, but still quite close to the underlying infrastructure. So what we've been trying to do is work, as it were, from the top down, rather than abstracting from the bottom up, work at the level at which problems are expressed. So just a few slides by way of justification of domain-specific languages, both in general and in the case of what we've been looking at. So what you try to do is write programs at the level of the user rather than the level of the machine. Now, of course, it's a false dichotomy, but the aim is to push them further towards, as far as you can, towards the user, so that what they see expresses things in their discourse rather than in a language closer to the machine. And I think working with a DSL allows you to do some things. Of course, you restrict what you can say. You can just express things in a particular area. But it does allow you to do some very positive things. It means that some mistakes become impossible. The language doesn't allow you to make those mistakes. It's Orwellian in that sense. It controls what you can do. And because it's working in a more restricted area, it makes analysis a lot easier and also potentially more accurate, because you know what your programs are, you know the domain of your programs. You're not trying to analyze any old program. You're analyzing programs written in a particular constrained design. And it also allows you to design tools that fit the DSL. We'll see that a bit later on. So there are strong advantages with doing this. And of course, the disadvantage is potentially you can only express things in a language you've written. But you can avoid some of those problems by writing what's called an embedded DSL. So a DSL where you don't design the whole language from scratch standalone. What you do is within an existing language, in our case Haskell, you design a small language where you can selectively, if you wish, pull in features from the host language when you need them to express things in your DSL. So we have a DSL, we've embedded it, we can run the programs, but also when you have a DSL, you can do other things with it than run the programs. We were talking about this earlier on. You can simplify. You can say, oh, look, I've got this program. I can simplify it to this other program. Or you can make a valuation. If what we're doing is working with contracts, we can think about giving a value to a contract that will be run or is running. So having a language allows us to do other things than simply execute the programs. Okay, so that's why DSLs are a good thing. What about financial DSLs? Well, there's another Simon speaking in another room who was responsible for some of the earliest work in this area, which is now about 20 years old. So using a high-level, a functional language for describing financial contracts. So Simon Peyton-Jones and Jean-Marc Hébert and Julian Seward. That's one of the first papers which was written in this area. And they inspired other work which is perhaps more directly fed into what we've looked at. So there is a model. So let's look at what's in that model, and then I'll explain how we've modified that model to work in the blockchain space. So apologies, this is a simple contract, but it's one I can animate. It fits onto a slide. So, and you know, this is a financial transaction, right? Alice wants to buy a cat from Bob. She's got some money, he's got the cat. But neither of them trusts each other. But luckily, they have a friend whom they both trust. So we can build a contract that allows them to transfer that money safely. So Alice pays the money into the contract, and what happens is that Bob gives her the cat. They can agree that the right thing has happened, and Bob gets the money. But Alice could put the money in, and Bob doesn't give her the cat. We can see they disagree. Alice says she's done her bit. Bob won't give her the money. At this point, Carol comes in, and she and Alice can agree, yes, Alice needs to get her money back. And that's indeed what happens. And that embodies an awful lot of what's in a financial contract. Money is transferred, money is deposited, money can be transferred. Things can happen conditionally on choices made by participants. So simple programmatic actions. And here in a stylized contract language, you can see that contract described. When we wait for Alice to make a choice, and then Bob to make a choice, and if what they have chosen, they agree on what should happen, then we process it as an agreement, otherwise we arbitrate it. And the way we process an agreement is, if they've chosen to make a payment, then Alice pays Bob. Okay. So there's our simple contract. And the constructs you can see in here are the constructs of our language. And this, as you can see, is Haskell. Somebody made an unkind remark that it could be Lisp because of all the parentheses, but think of it as Haskell. We can wait for certain actions to happen, and when those happen, we do something. We can do things conditionally on certain situations, certain observations. We can make payments, and we can get to the end of the contract. So there's a relatively small set of things that we can do. So, yet when, as I say, enables the rest of the contract, we can do things conditionally. Sorry, this is just repeating what I said, and we can make payments. So what happens when we think of moving this onto blockchain? What difference do we have? Well, one thing we have to think about is, for an ordinary contract that we sign in the real world, we sign with a pen or we sign electronically, then it is enforced by a legal system. But we can think in this world, can we build contracts that will enforce themselves? Can we write things in such a way that they produce the behavior we want without having recourse to a legal system? Because if this thing lives somewhere in cyberspace, it's not clear in what jurisdiction, if any, it exists. So that's one of the things you have to think about when you move into this domain. Another thing you have to think about, which is in one way is the fundamental property of a blockchain, but in another is a limitation, is that one thing you want your blockchain to guarantee is that you don't spend money more than once. It has to guarantee that money isn't created out of nowhere, money isn't lost. But if you think, the financial system in which we operate is one where double spending is the norm, because that's effectively how credit works. So if we are doing pure blockchain contracts, we have to think about some things from a slightly different perspective. And there are some things which don't necessarily make sense when you want to move them into this model. There's also a question about how the contract will operate. So the running contract can make some things happen. It's a program that's running on a distributed environment. We can ensure if the contract says a payment should happen, the contract can make that happen. But other things, the contract, of course, can't do, because there are participants. Somebody who's participating in a contract may have to deposit some money in that contract. The contract can't force them to do that. So there is there can be a difference in modality. We can push a payment, but we have to pull in a deposit. And there's also two sorts of correctness question we have to think about. And this is one of the places where we have to change the way we think, or we have to think about the model quite closely. We have to avoid bad behavior. We have to avoid double spending, for example. So that's, if you like, a safety property stopping bad things happening. But there are also liveness properties which we want to guarantee. We want to make sure that good things do happen. And we have to think about that. We also have to think about how these contracts will interact with the outside world. They might depend on the price of oil at a certain point. They might depend on random values. So we have to think about how to deal with those, what are called oracles. I mean, from an abstract point of view, we can think of those things really as another participant taking part in the contract. But technologically, in engineering, with an engineering hat on, we might want to think of these as in a different way. So one of the things that we need to guarantee in this sort of context is what we call commitment. We need to be able to say to somebody, if you put some money into a contract, we can guarantee that that money will not be locked up forever in the contract. It might be paid to somebody else, but we want to be able to guarantee that after a finite amount of time, if nothing else has happened to it, you get the money back. So we need to avoid somebody walking away from a contract. We don't want to be able, I pay some money in, you're meant to pay some money in, you just walk off. My money could be locked forever. So we need to build into the way we design our language, our contracts, avoiding walking away. But also, in order to guarantee this liveness property, if we're asking for a deposit, we ask for one and we can't wait forever. We have to ensure that after a fixed amount of time, the deposit has to happen or something else takes over. So we finish up building into our model a notion of timeout. It's not rocket science, but it's the thing that allows us to ensure we can deliver on this property of money being committed for a finite time, and we can also ensure that progress happens. So what we do, for example, with our and just giving you the slightly more general syntax, we can, when we're waiting for something to happen, we can wait for multiple things, and the first one of those to happen we go with. What if none of them happens, ever? What we have to do is we have to add some sort of timeout and say, if the timeout happens, then we do whatever this contract says. And what this says is just refund everybody's money. So that's what we do with actions. And for commitments, we do a similar thing. So we say, we wait for Alice to make a deposit into her account. But again, we can't force Alice to do it, so what we have to do is wait for her. We wait up to slot time 40, if you like, and then we close the contract. So again, what we do is, we have a very simple core language here. All we're doing is saying, when we're waiting for something, we only wait a finite amount of time, and we have a remedial action to take. Okay, so that pretty much covers the example, and this is our language. It's a Haskell data type. We've got close a contract, give all the money back if there's any left, making a payment from an account to a payee, doing something conditionally on that and choosing one of these continuations, waiting for a set on a list of actions, a list of cases where each case is triggered on an action and has a continuation contract, and we've got a thing for capturing a local value. So that's our language. And I think I've explained this pretty much informally. Close does the refund, pay makes a payment, if is a conditional, and when is the case which allows us to wait for an action and do a corresponding contract, and then after the timeout we do whatever the timeout case was. Okay. In this, so we've got a simple set of contracts. We've got some other values in here, some other data types in here. we've got a type of values, we've got a type of observations, we've got a type of actions. Perhaps the most interesting of these are the actions. We can wait for somebody to deposit some money. We can wait for somebody to make a choice from a range of options. And we can notify an observation from a participant off the blockchain. And then observations just allow us to compare values, and values are values. So we've got a small core language. So this is our language, and in a nutshell what we have an embedded domain-specific language, so a very small Haskell data type where we can write contracts using selectively Haskell features. It's designed, it's got an executable small step semantics, which is written in Haskell. We've also got a version in Isabelle, so we can prove properties of contracts in Isabelle. It runs on this UTxO blockchain, so on a Bitcoin style blockchain. It's extended slightly to allow us to pass some data when we make a transaction, which is a bit like covenants in Bitcoin, if that makes any sense. And the way that the contracts are executed is that we run an interpreter. We have a little language for Marlowe, and Plutus is the general purpose language, which again is really just Haskell, that runs on the blockchain, or is compiled from Haskell. And our interpreter, we have an interpreter for Marlowe contracts that runs as a single Plutus smart contract. So at the moment, it's the largest smart contract that's running on the IOHK blockchain. So we're able to run these things in a very transparent way. You can see that the code for the code that runs on the blockchain is effectively the small step semantics. So we have a functional model of how these things execute, and that itself executes on the blockchain. And some things I'll say, I think I've got time to say a bit more. We do some analysis using Z3. So we're able to provide analyses of the behavior of these contracts. And I said, we've done some early work in Coq, so that should say Isabelle. And we've got an environment for, so that you can simulate the effect of one of these contracts. So as I said, it's implemented on this blockchain, and the interpreter is a single Plutus program. I mean, what we have to do, just in a tiny bit more detail, we have to produce code that runs in a user's wallet, and we also produce code that builds transactions that get put onto the blockchain. And typically a transaction will consist of a number of inputs that have come from the Marlowe inputs and a number of payments. And those get coded up into a single transaction, one of those boxes on the blockchain by the interpreter. But that's a tiny language. That's really just a core language. And it's got simpler than it was a few months ago. So we've been trying to simplify it. How do we write real contracts? Well, the answer is we use the embedded nature of the DSL. So if you look at this example, everything in purple is in fact defined in Haskell, because we can write simple abbreviations. In Haskell, we can write simple functions that extend. So we can say this thing that tests whether something is a payment, it checks its argument against a particular constant. So we can selectively use very simple features of Haskell, effectively definitions of constants and definitions of simple functions, to allow us to write readable contracts. But the language design we've had to put into this is really quite minimal, because we're running on the back of Haskell. Now you could, and this is a possibility, we could say in future, well, we'd like to have a standalone version of Marlowe. And I think at that point, what we would have to do is say, we take Marlowe as it is, and we embed it in the bits of Haskell that we've seen we need from these early experiments. So we'd extend it to support the things we need here and here. And there's a longer That's the code to deal with arbitration. So we're able to write these things in a top-down sort of way. But of course, all these things are simply abbreviations, so we're able to generate a pure Marlowe contract from these, which you might call compilation or elaboration or whatever. So these are simply abbreviations which allow us to write in a more readable and maintainable way. So what we've taken as a test for whether we're on the right track is to take this financial standard by ACTUS. What they have there is, there's their website, they have a taxonomy of the 20-odd standard financial contracts as they see it. And what we've done is look at a series of examples from across that. So one of the simplest contracts that they've encoded is what's called a zero coupon bond. It's financial ease for making a loan, effectively. So it's an issuer issues a bond to an investor, and what they get when at the start date, they get the money from the investor, and what they have to do at the end date is pay that money back. Now, for it to be worthwhile for the investor, they get the full, as it were, the notional value of the bond minus a discount at the beginning, but they have to pay back the full value at the end. So it's a simple, one of the simplest financial instruments, but it's effectively a loan. So it doesn't pay interest, but it gives you a profit when it matures. Now, I said what we wanted to do was think about making these self-enforceable. So how could we do that? Well, one thing we could do is we could say that the issuer, the person who wants to borrow the money, has to make an upfront commitment of the money that they're going to pay back. But that's just ridiculous. If they've got the money, they don't need to borrow it. So that doesn't make, we could code it like that, but it would make no sense. The second thing we could do is we could say, well, the investor simply takes a risk. That's how things are in the real world, that if investors don't always get their money back, we can write the contract where that risk is possible. But a third way we can do it is that we can have a third party in the contract. And this is one place where we differ from the way that the Simon Peyton-Jones and colleagues wrote their contract languages. They were all contracts between two people. Many financial contracts will involve multiple participants, and we've done more of the work from the Copenhagen School, where they've got multiple parties with their contract. We introduce a third party who's the guarantor. So he or she provides a guarantee that the money will be paid back to the investor. And if you like, what they're doing is analogous to collateral. And I'll say a tiny bit about a fourth approach at the end. But let me show you, here we've got the guaranteed zero coupon bond. So this is the contract where we do have a guarantor. And so the question here is, this language is designed for people who are coming from a financial background. You might say, well, this is ridiculous. This is really for programmers. But I think you look at this, the style of this is something which is relatively stylized, choosing appropriate names and so on, makes pretty clear what the contract is doing. So you can see here we've got the type, it tells us that there are 3 parties involved, 2 values, 2 timeouts, and they give us a contract. And you can see the parties are issuer, investor, and guarantor. We've got a notional value and a discount. We've got a start date and a maturity date. So we've got a template, if you like, there for what one of these contracts looks like. So function equals template. And then you can see that what do? We wait for the guarantor to put money into the contract. And then we wait for the investor to put money into the contract. The guarantor puts in the whole value, the investor puts in the notional minus the discount. If either of those things don't happen, we just refund all the money. If both of those things have happened, we wait until the start date, and then we immediately pay the investor. From the investor, we pay the issuer. And then we wait for the issuer to pay back the investor. If they don't do that by maturity date, then the guarantor makes the payment. So that's pretty much, it's slightly different syntax, that's pretty much expressing what I said before. And we've seen that we're able to produce contracts in a similar way, ones which have a much more complicated schedule of payments, for example, using the Haskell embedding plus the core language. What you're seeing here is just pure Marlowe. Okay, so we can, how much time have we got? We've got a way of working with this online. We've got this thing called the Marlowe Playground, which is a web-based, browser-based tool that allows us to develop contracts in Haskell, convert them to Marlowe, simulate them, analyze them, and also we can develop them in Blockly too. And there's the URL. But it's always a bit more exciting if people try to show things as they are. So here it is live. Let me just reload. I hope I'm still connected to the internet. Yes, okay. So what you see here is we've got three tabs. We've got a tab for a Haskell editor, we've got a tab in which we do the simulation, and we've got a tab in which you can create these contracts in a visual language, a bit like Scratch. And this is, we can talk a bit later on about the rights of choice of language. What have we got here? We write programs in a Haskell editor. It's giving us Haskell. We can use the Haskell syntax. We're getting Haskell syntax highlighting. And in the environment itself, we're able to compile these programs into pure Marlowe. So we can take that, and you can see now we've compiled that program, the program up here, using a whole lot of abbreviations into something that is a pure Marlowe contract. Now we could move that to the simulator, but I've actually got a slightly smaller contract in there. And what we're able to do in the simulator is single step, but we're also able to do a static analysis. So if I click this, you can see we get a failure here, and we get quite a lot of information. But what we get, the crucial thing, you can see at the bottom here, if you can read it, it says there's a transaction partial payment. The contract is supposed to pay, it's supposed to make a payment here, and there isn't enough money in the contract to make that payment. So we're able to do it. This is where we're using Z3 in the cloud to give us this analysis. So we can check, now if I change, and that's because I didn't put enough money in the contract to start with. If I change that to 12, say, and redo the analysis, it should pass. So we're able to do that sort of analysis. But we're also able to simulate this in, let me just reload this. We're also able to simulate this, and you can see that inside the simulator, we get suggestions about what inputs can be made. So because we're in a DSL, it's easy to see that what the contract is doing, sorry, if you can read this, good luck, well done. It's waiting for a deposit of money from Alice of 12 Lovelace. And this is what we're offered here as part of our input. So we can include that in our input. We can apply that as a transaction. And then you see that we now have, inside the state of the contract, we've got account 0 for Alice, has those 12 ADA in there. And then what we're asked to do here, Bob has to choose a value, and if Bob chooses value 1, that could be made. So now you can see what's happened is that Bob has made that choice, and once Bob made the choice, what we do, he chose the value 1, what we do is play that value plus 1 to Bob. So he's got 2 Lovelace, and Alice is left with 10. So and if we want to, we can undo this. So we can step forwards and backwards through the contract. So what the aim of this, and I think this is one of the nice things about a DSL, is that we're able to give people a lot of assurance about how contracts run, because they can interact in this kind of, they can simulate them in this kind of interactive way using this environment. And they can also get these guarantees. So for example, the guarantee that we saw here, that there was no, let's have a look. Now, you can see that this contract, the analysis has failed, because what I'm doing here is analyzing the contract here, which is one without the surrounding commitment. So it says, actually, there's a payment here that can't be delivered. Now we could, what we haven't done is integrate what we do with the state and what we do with the analysis, but that's entirely possible. So that's, if you like, it's reflecting a sensible output for the contract, but not for the context it's in. So that's work in progress, as it were. Now let me show the final thing, and that is using Blockly. So I think this is, we wanted to provide a mechanism which was really programming free. And this is what we've got. So you can now build up a Marlowe contract simply by putting together these templates. So we have, for each kind of contract, there's a template. We can slot them in appropriate ways. We have a constant value there. We can stick that into there. We have a payee, so we could choose to pay. And then we have to give a name, so we can say Alice. So we're able to build up a contract without writing any programs at all. And arguably, that's a very important way of, for a whole group of users, first of all, to learn the language, but secondly, to not be intimidated by what they see. And we're able to convert that to code. We can convert that to Haskell. Now, we can't do it here because there are bits that are still to fill in. But if I pull that out and put in just a closed contract, just for the sake of argument, let's put in Bob here, we should be able to convert that to code. Oh, no, we can't. Why can't we do that? Oh, let me delete this. Oh, never do live demos. There we are. And now you can see the contract we have in the simulator is the one that we had in Blockly. So we're able to move from the Blockly representation, and in fact we can go in the other direction. We can go back to Blockly, and you can see now that has been changed to Freedom. So we're able to so we can present these contracts as purely visual. We can present them as embedded in Haskell, and outputs from both of those can be put into the simulation environment and the analysis environment. So let's resume slideshow. That's where we were. I mean, these are slides that just show you the compilation, they show you the simulation. So these are really just backups in case the gods of the live demo didn't deliver. Here you've got this example I showed earlier on with the partial payment failing. And then if you change that value to 2, then you get the analysis working. And as I said, what we do is we use the SBV, for those who want to know what's going on under the hood, there's the SBV binding of Z3 in Haskell. We use that and throw the problem off to Haskell and Z3 running in the cloud somewhere. So it should be, touch wood, it should be scalable. We spin up an instance for each analysis. And we're able to do a full search of all the state space. So we're doing model checking, if you like, using an SMT solver. We've also done some formal verification in Isabelle. Here that you can see we've got a version of this semantics, the executable semantics in Isabelle. Now you could say, oh, that's awkward. You've got the semantics in Haskell, you've got the semantics in Isabelle. How are you sure that they're the same thing? And the answer is what we do is we extract Haskell from the Isabelle and then do a random test to see that the extracted code has the same behavior as the original code, using effectively quick check. What are we able to prove? we can prove, for example, we can prove that the money inside the account, the money inside each account in the contract is never becomes negative. This is something about computing transaction being quiescent. We can also prove that the amount of money at the end of the contract is the same as, so we can prove money in equals money out. So we have these very general properties of how our semantics works. And one of the things on our to-do list is to look at proving properties of these templates of particular classes of contract. So among the things that we want to do in the next few months, well, people react to the Blocklis or Haskell in a number of ways. One person said, nobody will use this until you can write these things in natural language. Other people say, you need Ruby syntax, you need Python syntax. I think one thing we can do is render these things in natural language. I don't think we want to start parsing natural language. I think the added value of that is tiny. We're working to complete the set of ACTUS contracts, and in order to do that, we need to do two important things. The way the contracts are set up at the moment, they have a fixed set of participants, which don't change. What we want to do is effectively tokenize those roles so that I can sell my role in this contract to you. Or indeed, I can sell a part of my role in this contract to everybody in the room. So you each get a token that represents that proportion of the running contract, so that these things can become actively tradable. We've got the infrastructure on the blockchain, so it's a matter of working out precisely how to design a layer on top of what we have in order to support that. So what we're doing is at the moment, we're running on a simulated blockchain, but in the next 6 months, again, we have to embed it for release in about 6 months' time. We have to integrate this with the full blockchain, and that will make us think again about oracles, for example. And we want to do some more proof. So there's a whole lot of things to do, but I hope you've got a sense of what we've been doing. And I suppose the takeaway message is, in this particular case, building a DSL seems to have been very fruitful. You know, but I think we're in a situation where potentially what we can do is, I mean, maybe we won't be able to describe every possible highly exotic financial contract, but use them in this small language, we can describe 80 or 90%. And within that 80 or 90%, we've got all these extra tools that we couldn't have provided for the general case. So I think I'll stop there.
Thank you, Simon. Do we have questions? We have about 2-3 minutes. Anybody? Yes?
Yeah. I mean, at the moment, we're looking at Cardano is a non-permissioned blockchain, so we're looking at how this works in that framework. We're talking to some of the ACTUS people about particular use cases, but we're certainly not bound just to work on Cardano. So Marlowe, we've got an experimental implementation of Marlowe on top of Ethereum, which is it's a slightly different model. You have to do things slightly differently, but in principle, it works in that domain as well. Yeah.
30 seconds.
Anyone?
Why not Lisp?
Sorry?
Why not Lisp?
Well, you've got all the brackets here, but you've got type checking as well. So you know you've got. It looks like Lisp, but it's type checked. So what could be better?
Okay.
Okay.